Okay, there we go. There is something really odd with my OBS. For some reason, whenever I switch from one scene thingy to another, my audio just goes really weird, so I just have to stop the stream, close OBS and start again. It's a little bit annoying, but I'm not totally sure how to fix it. But anyway, that doesn't matter. Okay, well, here we are. So, to start off with, well, so please do share any questions, comments, etc. in the chat as we're going along. But for now, what I'll do is I'll start off with some questions I've stolen from Reddit. So these aren't ones that were posted to me, they're ones I've just stolen from r/AskPhysics that I thought were quite nice, or ones I could answer in a nice way or pretty quickly. So there was one I saw that says, how do quantum particles know when they're being observed? So I think this is a big sort of misconception people have about quantum mechanics. Observation, the word is quite sort of, what's the word, like anthropological or anthrocentric or something, but it's got nothing to do with people. It doesn't matter, if it's a conscious thing or what that's observing it. An observation in quantum mechanics is a more physical thing. It doesn't necessarily mean looking at something. But in order to make a measurement of something, that's what observing means really. It means to try and extract some sort of information out of a system. You have to interact with it in some way. So to measure, the position of a particle, say the measure of the position of an electron, you have to fire a photon or something at it. And by firing a photon at it, you disturb that system. So you do affect it. And you can think about the Heisenberg's uncertainty principle in this way, actually. So the uncertainty principle says that the uncertainty in your position and the uncertainty in your momentum that you measure for a particle are very closely linked. And the way they're linked is in this expression, this uncertainty relation. And if you look at this expression, it tells you that the product of the uncertainty on the momentum of a particle, when you make a measurement, times the uncertainty on its position is always bigger than a constant. So this is h bar, Planck's reduced constant over 2. Sometimes people write it as h over 2. I think it doesn't really matter. It's just an order of magnitude thing. So in other words, if you make a measurement of a particle where you know its position very accurately, that means necessarily you know its momentum correspondingly less accurately. The better you know the momentum of a particle, the worse you know its position, and likewise, the better you know its position, the worse you know its momentum. And you can think of this sort of in terms of microscopes and like firing light at stuff. So if you imagine you're trying to figure out where an electron is, well, in order to do that, you need to have some sort of interaction with it. So you have to fire a photon at it and see, where this photon will bounce off at, where it will interact with it. And in order to get a more accurate measurement of the position of the electron, you would use a higher frequency photon, or you would use a smaller wavelength light. This is why when they do things like electron microscopy, where they use electrons instead of light waves to look at very sort of detailed images of cells, the reason that's useful is because the sort of effective wavelength of an electron is much, much smaller than the wavelength of any light particles. So you get a higher resolution. Resolution goes sort of with 1 over the wavelength of the thing you're measuring the object with. So the lower wavelength photon you use, the better you can resolve distances and positions, so the better you know where the electron is. But if it's got a lower wavelength, it's got a higher momentum. And if it's got a higher momentum, when it collides with this electron, it's going to disturb its position much, much more. So by using a higher momentum photon to measure the position of the electron, you create a bigger sort of, you create a bigger knock on the electron. So now the electron has picked up some momentum. So you know its momentum less well. It's sort of one way of thinking about it. So that was quite a nice little question. Feel free to post anything in the chat as I'm going along. There was another one from Reddit which was quite interesting, which is quite a long question. I'm just checking. Have I got my chat open on there? I do. Yeah, okay. There's nothing in there yet anyway. I was just checking. I wasn't sure if it was on the stream. So someone posted a really long question on Reddit about extra dimensions and gravitational waves. So they were talking about, well, they give some background and then they say, Theodore Kaluza calculated Einstein's equations in 5 dimensions, showing that extra dimensions have to unequivocally exist in order for the math to make sense. So much so that in 1939 Einstein said that extra dimensions don't necessarily have to be immaterial, giving succession to M theory 11 dimensions and superstring theory 10 dimensions. Well, so some background on that. This thing they mention about Theodore Kaluza and Einstein's equations in 5 dimensions. This is a really... that is definitely what I'm saying, yes. But thank you for the question. No, I think physicists should try and separate elements of consciousness and elements that depend on human experience from our equations. Things don't depend on humans in that way. I mean, sometimes people make arguments like the anthropic principle, but that's more sort of metaphysics than actual physics. Real physics shouldn't depend on things like that. But thank you very much for the question. So they were talking. This person on Reddit was talking about 5-dimensional Einstein's equations and this thing that by Theodore Kaluza. So this is called Kaluza-Klein gravity or Kaluza-Klein theory, and it's a really interesting thing. So if you take Einstein's equations are the equations that tell you how gravity works. They tell us how space-time sort of bends, how matter influences space-time and bends it, and then how things move in bent space-time. So it's Einstein's way of explaining gravity. And if you take Einstein's equations, which are, in our universe, of course, there are 3 spatial dimensions, and then in relativity we tend to think of time as being the 4th dimension. If you take these equations and you add an extra dimension, an extra spatial dimension, so now you've got 4 spatial dimensions and 1 time dimension, so a 5-dimensional theory. If you do that to Einstein's equations, to Einstein's gravity, you can show that this is actually equivalent to ordinary 4D gravity, so the gravity that Einstein was trying to explain for our universe specifically in 4 dimensions. And you also get electromagnetism out of it. So the theory of how magnets work, how electric fields work, you get this out for free from 5D gravity, which is pretty incredible. It seems pretty bizarre that electromagnetism is sort of hiding inside of 5D gravity, but that is what comes out. Now, there are problems with this. You don't only get electromagnetism out, you also get an extra field that you don't want. You get a dilaton field. And this is not something you want, because it's not something that fits into present sort of normal theories of physics. So it's an extra field you can't get rid of, which is an issue with this Kaluza-Klein gravity. But it's a really fascinating idea, and there are lots of models that still use extra dimensions where all this stuff is relevant. This Kaluza-Klein decomposition of fields. You can show, I think I mentioned a couple of days ago or something, if you add extra dimensions to space-time, where these dimensions are kind of curled up, so they're not dimensions you can't sort of look in this direction, but they're on very small scales, so you can't observe them because they're very tiny, and they sort of curl up on each other. So if you walk around in this 5th dimension a little bit, you get back to where you started. You can think of them as little circles at every kind of tiny zoomed in point of space. But if you add these extra dimensions, you get a whole host of new particles. In fact, you get infinitely many particles, all of sort of increasingly higher masses from all of your original particles you started off with. You get these so-called Kaluza-Klein modes. which nobody has observed any things like this, but because they get higher and higher in energy, and therefore higher and higher in mass as you go up, it's possible they're just at energies we can't measure yet, which is what is hoped. Then this person also talks about M theory, superstring theory, etc. So string theory actually requires that there are 11 space-time dimensions. This is a requirement for string theory to be self-consistent. And again, you can think about these extra dimensions. The reason we know that we can't rule it out immediately. So, you could very well ask, like I've said before, well, where are these extra dimensions? We don't see 10 dimensions around us. We don't see 10 space dimensions. We see 3 space dimensions. And the way of getting around that is to have these 7 extra dimensions very, very tiny and sort of looped up on each other. So we wouldn't be able to see them. Their presence wouldn't interfere with everything we see around us at a normal scale. But they will have important consequences for very high energies and very small scales. So that's a little bit separate, the string theory stuff they're talking about. And then this person is talking about what they think is a paradox. And they say, when we finally started using LIGO and Virgo to study gravitational waves, it seems that gravity is supposed to leak into other dimensions in order to prove that other dimensions do in fact exist. We have no amount of gravity to have leaked, so then my paradox question is precisely this. Were the last 100 years of physics misled by the false assumption of extra dimensions, which is highly questionable, or are our studies on gravitational waves via LIGO/Virgo wrong? Well, firstly, extra dimensions haven't really been going for the last 100 years. They've not been a popular idea, and also they're not sort of mainstream physics, really. In terms of very high energy physics, so trying to come up with unified theories, I think pretty much all the best contenders do have extra dimensions. So string theory being probably the most promising unified theory, definitely involves extra dimensions. But I think, I don't know what... So the person is talking about gravity leaking in extra dimensions, which is an analogy sometimes people use. So I understand this in terms of one of these extra dimensional models that I study. So the model I study is called the Randall-Sundrum model, where the universe has one extra dimension. So in total it's 5-dimensional. There are 4 space dimensions and 1 time dimension. So the way this model works is you have 2 3-spatial dimension branes, and connecting between them is an extra dimension, is a 4th spatial dimension connecting them. And I know this isn't a 3D thing I'm showing here, it's a plane. But the problem is you can't think in 4 dimensions, so you have to use a lower dimensional analogy. And one brane here, so this you could call the IR brane, or the visible brane, has everything we see in the universe associated with it. So all of the matter fields, the standard model fields, etc. are all localized to this 3D region of space. But then outside of that, there is a brane over here that's sometimes called the UV brane, which is associated with all these different higher energy phenomena. And actually it turns out gravity is strongly localized towards this thing. So everything is confined to this 3D brane where we see everything, we see this 3D universe around us now, except gravity. Gravity is allowed to exist in this extra spatial dimension. And it turns out that if you do the calculations, the wave functions you get for the gravitons are very strongly confined, or very strongly localized to the hidden brane, the 3D brane, the 3 brane that is not everything we observe around us. And that has the effect of meaning that gravity is very weak on our own visible brane. So it explains why gravity is weak. I sort of don't really see the analogy of leaking, but it explains that gravity is weak because all the sort of gravitons that are allowed to exist in these 4 spatial dimensions are localized away from the brane associated with our energy scale. So that's how it explained it's weak. But this is certainly not, there's so much physics that goes on that is not related to grand unified theories and higher dimensional models, that I think to say the last 100 years of physics was misled by these false assumptions is not totally fair to say. And I also don't know about whether LIGO or Virgo, whether measurements of gravitational waves have ruled out any of these things. I mean, I'm pretty certain they haven't actually. But that was an interesting question. And I mean, these higher dimensional models are really fascinating. Let me know what you think. Let me know if you have any general questions about higher dimensions. I mean, it's pretty difficult to think about these things, but it's interesting nonetheless to think about them. So there was another question from Reddit, which was slightly more technical, and it was about complex locuses. So they say in this question, you've got a complex number z, which is a function of another complex number w, and w has real and imaginary components u and v. And the point this question the person asks is they want to sketch the locus of z when u equals 0 and v is allowed to vary. So first of all, u is 0 and v can be whatever we like. Okay, well, if u is 0, then that just means w is iv. It's a purely imaginary number. Well, we can put w back into z, and when you do that, you get minus v squared minus 2v. Being very careful of the fact that when you square the imaginary unit I, you get minus 1. That's why it's called an imaginary number. Real numbers don't act like this. So you can write this now slightly differently in this way. So immediately you can see that z has no imaginary part. This is a purely real number. So when we're sketching this on the complex plane, it's pretty funny wonky axes I've got there, where we have the imaginary part of z up here and the real part of z here, everything is just going to lie on the real axis. There's nothing in the imaginary axis. But then we have to ask whether it covers the entire real axis or just part of it. So I think it's useful now to sketch the real part of z against v. And then we can look at the range of values the real part of z is allowed to take for all the different values of v. So this is a quadratic. It's got a root at v equals 0 and a root at v equals minus 2. And now because it's got a negative in front of it, it's also going to be an upside down quadratic. So it will look something like that. So you can see immediately that it doesn't actually cover the entire range of possible values for real z. It only covers everything from here below. So now we just have to find what this value is. Well, if this is minus 2, this is v equals 0, then from symmetry you can say the peak here is at minus 1. So to find the value that the real part of z has, we just have to put minus 1 into here where v is. And that just gives us the real part is plus 1. So in other words, the real part of z is allowed to take values from plus 1 just down to minus infinity. Okay? So we can sketch the domain like that, where that is plus 1 there. So that was pretty straightforward. Imaginary numbers are interesting in general to think about, though. I think it's a slightly deceptive name to call them imaginary, because there's nothing less real about I than there is about the number 1. Numbers are abstract, I think, by definition. You can point and say, look, there's one apple or something. So you have an analogy that links things to the real numbers, but having, I think, even continuous numbers. I mean, the real numbers are continuous. Continuous things in nature are not immediately obvious. I mean, if you think about atoms and you think about breaking things down to their fundamental constituents, nothing is continuous. It's always made of bits of stuff. Unless, I suppose, you start thinking about the quantum field that make up all that matter, then I suppose you could say those are possibly continuous, possibly not continuous. It depends. I think some people, there are some ideas that space-time itself might be discrete. So you can't, there are tiny invisible grid lines in space-time. So you can't have it's not a continuous flow from points to points. There are grid lines set. In which case, I think probably, fields, also quantum fields that make up matter, also wouldn't be continuous. So it's not unreasonable to say that the idea of a real number, which can take any continuous value, is also an unnatural idea. So with that in mind, why would you possibly say that imaginary numbers are unnatural? Imaginary numbers are completely indispensable in quantum mechanics. And quantum mechanics is closer to the real guts of what goes on in the universe than classical mechanics is. So classical mechanics, you can avoid using complex numbers pretty much for everything. Complex numbers make things a lot easier in parts of classical mechanics if you're dealing with oscillatory motion and stuff. But in quantum mechanics, it's pretty unavoidable. I'd say it is unavoidable that you need to deal with complex numbers in quantum mechanics. So really, it seems to me that imaginary numbers, complex numbers, are more natural, or at least as natural, than real numbers. If we're going along this sort of philosophical viewpoint on it, what does everyone else think? Are imaginary numbers imaginary? Do you think they're, I'd be interested to hear what other people think. I'm sort of running out of problems, so please do ask anything in the chat, or else I will just have to start talking more nonsense about philosophy of numbers. I mean, it's an interesting question in general about what is more fundamental, maths or physics. I think the default is probably maths is more fundamental. Certainly maths can describe a lot of things that physics can't, that you can't possibly imagine. Like extra dimensions we were talking about. It's impossible to think about a fourth dimension. You can't picture 4 dimensions, but it's totally trivial to write down an expression that describes 4 dimensions. If I want to, I can write down the equation for a 4-dimensional sphere right now. X squared plus y squared plus z squared plus w squared equals 1. Well, let's say equals r squared. That's a 4-dimensional sphere that has a radius r. Totally straightforward to write down. And then you say, okay, well now picture a 4-dimensional sphere, picture 4D space, and you can't do that. So mathematics is really sort of a crutch for things like that. But then, will the rules of logic and things like that, will they ever arise as a result of physics? Could there be universes where the rules of logic and things are different and distinct? I mean, it's certainly not something you can imagine. I can't imagine that, but I suppose in theory you also couldn't rule it out, possibly. Is logic a branch of physics, or is physics a sort of abstraction of logic? Who knows? Yeah, so that's my thought on extra dimensions. There was something else I was going to say about maths and physics as well, but I've forgotten now. Yeah, my brain has gone dead. I guess the question about whether maths is invented or discovered is also an interesting question. I don't know if I have a particularly strong opinion on it, though, personally. I mean, if anyone in the chat has an opinion, let me know. Do you think maths is invented or discovered? Though you are all very quiet today, actually, so I'm running out of things to chat about. I suppose probably I'd lean more towards it being discovered, but I don't particularly know why I would justify that. I suppose it always seems more fundamental than just a tool, which sort of makes me think it's more likely to be discovered than invented. I don't know, it's hard to think about these things, actually. There are ways you can think about higher dimensions, actually. Although you can't draw in 4 dimensions or picture 4 dimensions, you can picture sort of shadows of 4 dimensions. So, you know, just like you'd cop out and say that axioms are invented, but the consequences are discovered. Well, that's a very good point, actually. Yeah. But I suppose, I mean, it is quite difficult, though. The thing is, you can say that axioms are invented and consequences are discovered, but it's actually I think it's quite hard to come up with a set of axioms that are not self-contradictory. And I think the way, you know, our mathematics is constructed, where, you know, there is no contradiction between different axioms, you know. I mean, I don't know a great deal about the sort of foundations. Oh, there's a plug there. I should do that. The foundations of mathematics. But I think it's not easy to pick axioms that are not self-contradictory in some way. And I just wonder, I mean, there must be a lot of research on this, about the sort of the space of possible axioms, or the space of freedom of choice you have in choosing these axioms at a very fundamental level. That would be something I'd be interested in. I was about to say something else as well before that. What was it about? Oh, I was talking about higher dimensions and shadows. Yeah, so you know, obviously, if you're a person, you're a 3D object, but your shadow is kind of 2-dimensional. Well, if you were 4D, you could have a sort of 3-dimensional shadow. And I mean, obviously, I can't even draw in 3 dimensions. So what I'm going to try and draw now, let's try and generalize drawing cubes to higher dimensions. So okay, let's start off with a 0-dimensional cube. Okay, well that was easy. You probably can't even see it. I just drew a dot here. I mean, even this is a little misleading. This is supposed to be just a point. You know, a point is a 0-dimensional object. We might as well call it a cube. Though a point, you know, it doesn't really have any kind of a shape or or geometry. It's just a point. But that's our 0-dimensional cube. Okay. Well, how do you construct a 1-dimensional cube now? So now we're adding an extra degree of freedom. So now we take 2 0-dimensional cubes and we connect them up by a straight line. This is, you know, a 1D sort of image of a cube. Okay. And now, okay, how do you create a 2D cube? Well, let's take 2 1D images of a cube. This, you know, when I say a 1D image, I mean like what you would see if you it's a little difficult. So if you live in a 1-dimensional universe where you can only move backwards and forwards, the things you see would be 0-dimensional. Okay, so think about it in terms of 3D space. When you see something in 3D, in our 3D universe, you don't actually see in 3D. You know, humans don't view things in 3D. What you see is a 2D sort of plane of light coming towards you, and your brain fiddles around with things. It uses the fact that some things are shaded, some things are brighter, and it tries to construct a 3D image. But it's doing that out of purely 2D information. Okay, the information that comes into our eyes is 2-dimensional. It's just a sheet of light of different intensities on a 2D plane. Okay, so when I say a 0D sphere cube, I mean this is the cube you see if you live in a 1-dimensional universe. You see a 0-dimensional point. You know, you can only see points. Whereas if you live in a 2D universe, you can only see line segments. Okay, you've no way of looking above and looking on top of things. So like taking the flatland example, say this is flatland. this orange cube here. So here is Mrs. Circle. It looks like I'm drawing SpongeBob, but I'm not, I promise. Here is Mr. Triangle. And these objects, you know, when they're walking around, all the triangle can see from their perspective when they're, you know, looking out. So this is an eye here, just to show they're looking at the circle. All he sees from the circle is a line segment. He can't tell whether it's a circle or a square. Well, that's not a square. Or a square of the same diameter. Okay, they just see this one-dimensional image to them. Okay, so that's what I mean by zero-dimensional and one-dimensional here. So now let's think about a 2D cube, or just a square, as we'd call it. So what we've done is we've taken two 1D objects, and now we're going to join them up by other 1D objects like this. Okay, so now we have a 2D cube. Well, okay, let's generalize to 3D. Now we take two 2D cubes. Well, and now it's getting difficult. So now I need to move these into a third different direction to connect them up. So of course I can't really do this because I can't properly draw in 3D. But what I can do is I can draw them offset so that you take that as meaning I've drawn them like that. And then I connect up these corresponding edges by line segments. So then this is what we'd call a 3D cube. Well, okay, we seem to have developed a fairly general way of constructing higher dimensional cubes. So let's try it now for 4D. So now I take two 3D cubes. Well, I'm going to stack these a little lower. And I put these near each other. So I stack these in across from each other in a fourth direction, in the fourth dimension. Now, of course, we can't think about what this means to point in a fourth independent direction, but we can sketch it. So what we're sketching here is sort of a 2D shadow of a four-dimensional cube. So now all we have to do is, take the corresponding edges, not edges, vertices, and connect them up. And we'll get something pretty crazy looking. And what this is a 2D shadow of a 4D cube. So sometimes people call this a tesseract, I think is the technical name for it. Now this isn't not tesseract as in the space stone from the Marvel Cinematic Universe. Is the tesseract the space stone? I actually can't remember. I think it is. Someone will, a Marvel nerd in the chat, if one exists, will definitely correct me, but I'm not big up on that, so I'm not sure. Smashed it. Oh, brilliant. Thank you, Liam. Yeah, so I think tesseract is the name for a 4D cube. So this is how you can draw one anyway, which is quite nice, how you can generalize all of these things, starting from 0 dimensions all the way up to 4. Now, if you were really feeling very bored, you could try and draw a 2D shadow of a 5D cube. So then you would just take two of these tesseracts, plot them sort of near each other, and connect up the various edges and stuff. But I'm not going to do that because that sounds pretty messy. So yeah, higher dimensions are really interesting. Okay, so I have rambled a bit about real numbers, complex numbers, higher dimensions. What has everyone else been reading in the last week? I'm curious to know. Has anyone else been doing anything interesting? I haven't actually done much work today. I should have done a bit more, but I have mostly just been working through papers recently, as usual. So please do let me know what you've been doing in the last week or so, anything interesting you've read, or if you have any questions. I'm always very happy to take some questions. I might not be able to finish them, depending how hard they are, but I will give it a go. Something else as well I've been thinking about doing. I've been thinking about adding an additional day to the days on which I stream on Sunday. So I've been thinking about doing what I'm sort of calling in my head a Sunday spacewalk thing, where basically I'll get on Universe Sandbox. I don't know if everyone knows what Universe Sandbox is, but it's a pretty sort of nice little astrophysics-y simulator thingy where you can replace the sun with a black hole and see what happens to the solar system and stuff like that. But it looks it's sort of very graphically pretty. So I was thinking what I would do every Sunday would be to load this up and kind of talk about a few different aspects of space. So talk a little bit about each of the planets, and maybe then we can talk about black holes, talk about stars, galaxies, that kind of thing. That's my plan anyway. It probably won't be from this Sunday. I think I'll leave it a week because I have to think a little bit more about what I'll talk about. But let me know your thoughts, or if there are any spacey, astrophysics-y things you're particularly interested in. And we could see if we could take a look at those. But yeah. Universe Sandbox will break your CPU if you let it. Well, yeah, I won't turn the settings right the way up, or I won't try and simulate, like, I don't know, several thousand galaxies colliding. That would be quite messy. They do have a nice simulation, though, of the Milky Way and the Andromeda Galaxy colliding. That's a really nice little graphic they have. And I mean, if you're really bored, you could watch that happen in real time. Despite the fact, I think I can't remember how many billions of years it's supposed to take until the Milky Way actually does merge with Andromeda, but that'll be quite a while. So Liam has been doing some readings on big complex quaternions versus XYZ, how some physicists wanted IJK taught instead of XYZ as it makes stuffs like rotations and comprehending 3 dimensions to begin with. Oh, cool. But other physicists said it'd be too confusing to teach kids. I guess so, yeah. I mean, I think quaternions, actually Maxwell's equations, when they were first written down, I'm not too big on clear up on the history about Maxwell's equations. For those that don't know, Maxwell's equations are a set of, four vector equations that describe the electric field and the magnetic field. Well, let me write them down. Let me see if my memory actually works. So this is an obvious one. Well, obvious to remember, it's not obvious what it means. This just means that there are no magnetic monopoles. Well, according to string theory, there may be magnetic monopoles, but classic electrodynamics, there are no magnetic monopoles. Then this one... Oh, I'm going to forget the prefactors. Okay, the prefactor is... Now it's the density of charge, not free charge. And is it 1 over epsilon, or is it just epsilon? I think it's over epsilon, I'm pretty sure. Okay, so that's the other one. This tells you how the electric field sort of spreads out from charges that source the electric field. And then there are 2 others. So there is the curl of B is equal to mu naught I plus mu naught dE dt. Now, is there a mu naught there, or is it mu naught? I think it's mu naught epsilon naught dE dt, actually. I'm probably going to get these slightly wrong. And then the last one is that the curl of E is equal to minus dB dt. So these are vector calculus identities. Can you show an example of groups used in physics? I can talk about groups in physics in a minute. So these equations describe how the electric and magnetic fields produce each other, interact with each other, and how they behave on their own. And these are all written down, you'll notice, using sort of vector notation. So this is the vector grad operator. Here it's dotted, so it's a divergence operator. And all these lines underneath mean these are vectors. And this is the curl, it's called the cross of this nabla operator. So these all use this setup of vector calculus, but I'm pretty sure that when these were first studied by Maxwell and Faraday and others, they actually hadn't sort of invented this maths properly yet. Or maybe it had been invented, but it hadn't become mainstream to physics or something. So they didn't have these tools to write down these equations, which are pretty simple when you look at them. So they had to use then quaternions, I think, which Liam was talking about in the chat. So quaternions they have similar properties. So they have a group sort of structure, and they have this kind of non-commutative property. What was that? To my knowledge, people like Faraday weren't well versed on maths, but Maxwell was. Yeah, I think Faraday mostly self-taught or something. I think he had very little formal education, as far as I know. I know one of them did. I get this history mixed up, actually, if I'm honest. I can't always remember. But anyway, quaternions have this nice sort of non-commutative structure, which is useful in sort of producing things like cross products. So they were using quaternions instead of things like the curl operator somehow, because they have this similar property like cross products. So if you know any sort of vector calculus, you know that if you take these basis vectors and you cross them with each other, they have this kind of structure. Where if you cross the x direction basis vector that I've called I with the y direction one, you get the z direction one, and so on and stuff like this. And then there's another one that's just k cross I equals j. And if you switch them, you know from the property of the cross product that then j cross I is equal to minus k. So it swaps the sign. And I think the quaternions have this same structure. So I think if you multiply I and j, the unit quaternions, you get k. And they follow this same structure. You just get rid of the bar underneath because they're not vectors, and you get rid of the cross product. So they were used in this way to study these 3D rotations, and well, not in this case 3D rotations, but to replace these cross products. I think they wrote this stuff all out in terms of quaternions, which I mean sounds like a real pain. I don't know what Maxwell's equations look like in that form, but I imagine it's much less nice and compact than this form as I've written it here. Then Bradley says, can you show an example of groups used in physics? Yeah, so group theory is really important to physics. Group theory is all about symmetry. So a symmetry in physics typically means you have some sort of transformation, and when you do this transformation on your system, there's some property of the system that doesn't change. It remains invariant. So a simple example is, here is my system. My system is a ruler. And if I do a transformation on it, this transformation is rotating the ruler. So I'm rotating it in 3D space. Well, what stays invariant about the ruler? Its length doesn't change. If I can rotate it as much as I like, and its length stays the same. So there, the invariant property of the system is the length of the ruler, and the transformation is rotating. And this symmetry is represented by a group. So in this case, for 3D rotations, this group would be SO3. To look that up, if you want to look that up. So this is the group of 3D orthogonal transformations. Orthogonal transformations that preserve length. That's what the S means. It means it preserves length, basically. So that's 3D rotations. Well, then, if you think about other transformations, so if you think now about special relativity includes rotations, 3D rotations, but it also includes these Lorentz boosts. So you're allowed to mix up space and time in special relativity. And the group that corresponds to this is what we call SO1, 3. So this has slightly different structure to SO3. SO3 as a group, these transformations preserve the element ds squared is dx squared plus dy squared plus dz squared. So this is just, 3D Pythagoras. This tells you that a length, which you measure by taking, think about my ruler. If you want to measure the length of this, well, you have to find how far does it go along in the x direction, how far does it go along in the y direction, and then, presuming it also slightly goes into the page, how far does it go along in, well, I've not drawn it very well, but how far does it go along in the z direction? And then from Pythagoras, the total length of the ruler is given by the sum of these things, all squared. Well, in relativity, this is no longer the best invariant you have. Because you're now mixing up space and time, the invariant you have actually looks like this. So it has it has a time dependence to it. Now you have to consider the time coordinates of the two ends of my ruler. Okay. And the group that represents these symmetry transformations which preserve this length, this new sort of funky 4D length, is called the Lorentz group. So this group here, we would call the Lorentz group. And there's a lot more you can do with this. Group theory has real importance in particle physics. So there's a theorem, or not a theorem, there's a classification of fundamental particles that is called Wigner's classification of particles. And this says that every fundamental particle should be some irreducible representation of the Lorentz group. And a representation of a group is sort of just an object that is also that respects the symmetry of the group. The group is a sort of more abstract thing. The representation is how you get from the group to the thing you're actually transforming. If that makes some sense. It probably doesn't. These things are a little, they are a bit technical. They're difficult to talk about just overall. So Wigner's classification says that every fundamental particle should be some irreducible representation of the Lorentz group. And there are lots of different representations of the Lorentz group. And you can, if you go through the sort of group theory of this, you can find that there's what you'd call a spin zero representation of the Lorentz group. And this corresponds to scalar particles, things like, well, scalar particles are particles with spin zero. So this corresponds to things like the Higgs boson has spin zero, doesn't it? Is that right? I think the Higgs particle is spin zero. Unless I've gone mad suddenly. Someone correct me if it's not spin zero. I'm pretty sure it's spin zero. Okay, just wait while I Google this. It is spin zero, okay. Well, not all bosons are zero. I went temporarily mad then and forgot the spin of the Higgs particle. Not all bosons are spin zero, actually. They just have to be an integer. So the photon is a boson, a gauge boson, but actually this has spin 1. And the graviton, if gravity is well described by a graviton, which it's not clear yet how that would work, then that would be spin 2. So you can have higher spin bosons. It just has to be an integer. And then fermions are particles that have a half number of spins. So, a half, 3/2, 5/2, and so on. And these are also perfectly good representations of the Lorentz group that you can construct. So from group theory, you can construct all of these different possible particles you have that you can describe. And the way you construct theories in particle physics it always uses this Lagrangian formalism, where you write a Lagrangian for your particle theory, and then you can compute things like scattering amplitudes from that by a roundabout way. And your Lagrangian always has to be invariant under the Lorentz group, because the Lorentz group is the symmetry group of all sort of space-time transformations. So any theory you construct should respect that. It shouldn't violate relativity. Anything you write down should be consistent with relativity. So all of the things that appear in your Lagrangian should be representations of the Lorentz group that transform in the right way, so that your Lagrangian is invariant under these transformations. And by writing these things down, you get particle theories for all these different bosons and fermions and so on. And this all really comes from group theory. So those are like groups that represent space-time symmetries. Liam's just said he was doing spin representations today. Ugh. Yeah, I know what you mean. These are space-time symmetries, but there are other kinds of symmetries too. So you can have internal symmetries. So the quark model, for example, is represented by an SU3 symmetry. So, or rather, QCD is given by an SU3 symmetry. So this has a structure to it, a symmetry to it, and from working with this, you can get properties of quarks and how QCD works and how these interactions happen between quarks and gluons out of it. So group theory is really fundamental to this formalism of how we understand particle physics and other things. There's an interesting thing as well. So we've talked about symmetry and groups. Well, there's also something you may have heard of called supersymmetry. So symmetries are represented by groups. Can you guess what supersymmetries are represented by? So a symmetry is represented by a group. Can you guess what is represented by a supersymmetry? What represents a supersymmetry? Let me know if you have a guess in the chat. Algebras, algebra, yeah, I mean, groups and algebras are very related. I think sort of the more fundamental thing actually is the algebra structure. But so the point is, if a symmetry, yeah, exactly. They've said supergroup. Bradley said supergroups. You're exactly right. So the thing that someone subscribed. Oh, I didn't see the name. Oh, I'm very sorry. Oh, please do say hello. I just missed your name, and I'll say hello to you if you just subscribe. Sorry, followed, not subscribed. I keep getting the word wrong. Whenever I say subscribe, I mean follow. Different YouTube and Twitch terminology. But yeah, so supergroups are the things that describe supersymmetries. Hello, Circuit 007. Hello, thank you for following. What was I saying? And the whole idea of supersymmetry comes from this theorem called the Coleman-Mandula theorem. And this is about if you're trying to construct a group that describes all of your physics, so a group that describes the symmetry that your theory is built around, you're slightly restricted in that the group that represents all of this symmetry, all of this available symmetry you have in your theory, can only be a product of space-time symmetry, so like a Lorentz group or Poincare group more accurately. A supergroup is where all members have had... That's a good joke. You're probably looking at the wrong supergroup page. But anyway, this theory says the most general group you can have is for some space-time symmetry group, like the Poincare group, times by some internal symmetry group. You can't do better than that. You can't combine, for example, if you're trying to come up with a theory of, quarks and stuff that comes from a higher theory, you can't combine the Lorentz group as I've drawn it here, or the Poincare group, with SU3 into some bigger group. You can't do that. So physicists then thought, well, how can we sort of get around this to find some new physics? So they thought about this idea of supergroups as kind of generalizing the idea of a group. So if you do this stuff with supergroups, you get new representations that describe new particles in addition to the ones you had before in your theory. So you get supersymmetric partners for every particle you already have. For every neutrino, you get a neutralino. For every electron, instead you have an electron and then you have a supersymmetric partner, the selectron, and stuff like that. And I think this is all motivated by group theory, this idea of supergroups and how you can extend these things in the most general way, while keeping in mind this Coleman-Mandula theorem. But yeah, this is I don't particularly work in detail in supersymmetry, so I'm far from an expert on supersymmetry. But it does solve quite a few problems. I think it's pretty well thought that some higher theory, some unified theory, whatever it is, will quite likely be supersymmetric. At least I think that's what Susie people think. Does supersymmetry have any experimental evidence? No, not a jot. Not at all. Well, this is the thing. So, first, supersymmetry, sort of the naivest way to construct it, it looks like all of your supersymmetric partner particles should have, all of your particles should have supersymmetric partner ones of the same mass. They should have this mass should be in common between them. But that can't be true, because then we would have seen, we would be just as likely to see a selectron as we are an electron or something. So then you can shift things around. So now these particles should have higher masses than the ordinary electrons, ordinary quarks, and everything like that. And then it makes them harder to see. So that would explain why we haven't seen any of them yet. But I don't actually know what the current sort of experimental bounds are on supersymmetry, because again, it's not my area. I don't work on the experimental side of anything. But I'm sure that there are constraints from what we do know from collider experiments like the LHC. There are constraints about how heavy, or how light rather, these supersymmetric particles can be. But I don't know the exact constraints on it. But no, it certainly doesn't have any experimental evidence at the moment. But hopefully one day. It's a very beautiful theory. And I mean, if beauty is anything to go by, or how likely a theory is to be right, which, to be fair, has been quite consistent so far. General relativity, very beautiful theory, very successful theory. Quantum field theory, very, well, sort of beautiful, but also quite messy theory. Very successful. So maybe beauty is a good marker for what makes good physics, but who knows? And then Bradley has asked, what do I work with? Well, so I'm a theorist, so I stay away from experimental stuff, and I work on phase transitions in the early universe. This is sort of particle physics. QFT is quite beautiful if you stand back and squint. I would agree. So I work on phase transitions in the early universe, particularly the electroweak phase transition. So this is from energy scales where the electric force and the weak force are unified. And as the universe cooled, as it expanded, the energy scale dropped, temperature dropped, and then things are allowed to split. So the electric force and the weak force can split into the separate forces we see today. And I'm interested in studying how this actually happened, because if you imagine what this looks like, what you would see in the early universe are these bubbles forming. So within the bubble, you have a region where the electric force and the weak force have split, where you've had this symmetry breaking, and outside of the bubble you have the unbroken phase, where the electric and the weak force are still in the false vacuum state. And how these bubbles grow, how they collide, how quickly they're formed and stuff, is stuff that is not exactly known. And it's interesting phenomenologically because soon, I think, when we launch LISA, this is a space-based gravitational wave observatory, we'll be able to measure gravitational wave signals probably coming from these bubbles. So when these bubbles expand and grow, they can collide, and this can produce gravitational wave signals. And with LISA, we hope we'll be able to measure these, which is pretty exciting. So that's roughly what I work on. Well, it's 8 o'clock, so by the definition of an office hour, we've just about run out of time, but I'm going to attempt a raid, so we will see how that goes. I'm going to try and raid another physics channel called Physics O, who is streaming right now, and he's very good. So if I just click /raid and then put his name in, this should work. So we'll see what happens. If it works, thank you very much for joining. Please, if you type it, before I do that, if you type in !Discord in the chat, you can get my Discord link and you can join my Discord, where we can chat about physics and share some physics memes, and you can submit questions for next time, etc. Or you can go in my about thingy and join, and, you know, follow me on Twitter and submit questions and stuff on there. So yeah, please do join my Discord if you fancy it. And what we'll do now is we'll try and raid Physics O. I'll see how this works. I've not done it before, so we'll see what happens. But thank you very much for coming, everybody. See you all very soon. Thank you. Okay. Let's raid now.